Hi, in this chapter we're going to talk about msp430ware, and we're going to use it to control GPIO, or General Purpose Bit I/O. What we're actually going to do is blink an LED, but to do that, that means we have to know how to use General Purpose Bit I/O. That's the purpose of this chapter. This chapter begins with a little discussion about what driver library is. That's a part of msp430ware. Then we'll look at what GPIO is on the msp430 devices and talk about a couple of other things we need to get started with before we do our lab. In fact, here's a look at msp430ware. We're looking at this in the TI Resource Explorer, and you can see that it's a whole host of libraries and examples based around the msp430 devices. So there's a number of things in here, from the driver library, graphics library, USB stack, capacitive touch, and so on. We'll be spending most of our time again in this chapter and throughout this workshop looking at the driver library itself. In fact, speaking of driver library, you can see here's an example of driver library versus traditional coding. I'm not going to talk about low-level programming, programming ones and zeros at the processor level, but the more traditional way on msp430 devices is to use the header files. Every single msp430 device ships with a header and linker command file that define every register and every bit in every register. What you've seen from a number of TI processors, msp430 included, is in the last few years, is a driver library. And this is a set of functions that allow you to do those same things, control peripherals from an API. We've worked very hard to keep this API as minimal overhead as possible, so the goal of being what you might say lean and mean is very important to us. But what we really like is the readability and ease of use of the driver library. Not only is it pretty similar between all of the different microcontrollers that use the driver library from TI, but it just makes your code much more readable, which, at least from our perspective, is really nice when you come back a couple years down the road and have to maintain that code or make changes or understand what it means. So here's kind of a quick snapshot of a number of the modules that are in driver library. So whether you're talking about clocking or memory, analog using, for example, A to D converters, timers, or I/O, just about every peripheral has its own driver library module. The ones that we're going to be talking about here in this chapter are the WDT, the watchdog, and the GPIO. Okay, so looking at GPIO, first question would be, what are the different ways to program GPIO? It's hard for me to hear your answers in this particular case, so let me just go ahead and put them up and just touch on them briefly. We already talked about the one there, using specific device header files and linker command files. We looked at that in the Code Composer Studio chapter because we used a kind of a very simple example that was already provided for us there. In this chapter, we're going to look at driver library. A third solution might be Energia. Energia is the Arduino port for msp430, and one of the later chapters in the workshop covers that. Depending on which version of the workshop you have, it might be chapter 8 or chapter 9, but it's one of the later workshop chapters. The final one is Grace. That's a graphical driver library tool. At least that's the way I describe it. It only works with the Value Line and Wolverine devices as of today, but it gives you a graphical user interface and actually makes programming some of these devices extremely easy. If you're, for example, if you're programming one of the FR5969 devices with Grace, it actually outputs driver library code. So very convenient. At this point, we don't cover that in this version of the workshop, but if you go back to an early version of the workshop that was based on the G2553 Value Line Launchpad, you can find a chapter, in that case chapter 8, that covers this particular tool. So let's look at the GPIO basics. First thing, msp430 has GPIO ports. It could be anywhere from 1 to 12 ports depending on the device you're using within the msp430 family. Usually you could say that the more pins the device has, the more I/O the device has, the more GPIO ports the device has. So the msp430 is kind of built around 8-bit I/O ports. So we've got, like I said, anywhere from 1 to 12 of those. On those I/O ports, each pin is individually controllable. I can make it be an input or an output. In fact, the pins can also, if they're set up as inputs, could also be generate interrupts to the CPU. We're not going to talk about that in this chapter. As you can see, we covered that in chapter 5, but it is something to keep in mind and can be very handy. And then there's a number of registers that allow us to control these GPIO ports. Input, output, direction. We're going to be looking at those as we go along through this chapter. And just kind of the last thing to look at, you can see there at the bottom, we've got like an 8-bit I/O port, and you can see that in this case, each bit in a register correlates to a pin on the device. So if we're looking at I/O port 1, pin 0, well, you can see there's going to be a bit associated with that. We nickname that P1.0. So that's a common way to nickname pins on a device or bits in a register. So P1.0, P1.1, and so on. How do we make a pin be an input versus an output? That can be done with the pin direction register. That's the DIR register. By putting a 1 in the direction register, we can set that pin to be an output. If we put a 0 there, it's an input. So you can see there kind of in the lower middle of the screen, there's a register-based example. So we can set P1 dir, so that would be the dir register for port 1. We can AND it equal to 0x81 to have it set bit 7 in 0. So that's one way of doing it, and that's not a bad way. But it is a lot more readable if we look down below and we see GPIO set as output pin. Very obvious, but again, that ends up being very handy later on in our maintenance phase. So we just specify the port, and then we can AND together the bits or the pins that we're interested in setting up as an output. So anytime you use one of the driver library functions, you should be including the driver library header file. And again, we'll mention that later on. So now that we've got it set up as an output, how do I set the output? That's done if you look into the hardware of the device with the out register. We just put a 1 in the output register, as long as this direction is set up as an output, and then we get a 1 out on the pin. Put a 0 in the out register, and that's what we get on the pin. Once again, there's a GPIO function and msp430 for that, so GPIO set output high on pin. We also have GPIO set output low on pin. So I'm only showing one of the two here, but each of those allow us to control that output register. Now, what if we wanted to use an input? So in this case, it's a little bit more interesting. So the input pins, the GPIO input pins on the msp430 are like you probably find on most microprocessors. They're held in a high impedance state. That way, they can be driven high to a 1 or low to a 0. The problem with that is if you're not connecting them to anything or they're not being driven, they can float, which means they kind of just flip-flop back and forth depending on the electromagnetic environment around the device. While that, if you're not reading the pin, you might not think it's a big deal, but when the msp430 family, you know, one of the big values for it is low power. We want to have extremely low power types of applications. And floating pins consume power. So that's something we don't want to see. So what we've done is we've actually built in some resistors. When there's nothing driving the pin on the device, we can have it tied high or we can have it tied low through a resistor. So we've got a couple of things here to help manage that. Along with the P direction, specify that we want this to be an input by putting a 0 there. We're going to read the value on the P1 in register. Okay, so that's going to be either a 1 or a 0. And if we want to use one of those resistors, the P1 resistor enable bit allows us to specify that. So the P1 ren allows us to say we want to use a resistor, and then the P1 out, well, let's see, why would we need an output? Because this is configured for input. Well, we can reuse that output bit in this case to specify whether we want to use a pull-up resistor or a pull-down resistor. So we get a little tricky there with that. Down below we show you the driver library code. So we're going to create just an unsigned short example here where we have a variable. We're going to set equal to 0. Then we're going to set our input pin with pull-up resistor. Oh, that's nice. Now I don't have to know about P1 dir and P1 ren. It's nice to know that they're there, and sometime you might want to go read their values in those registers and see how they're set. But we don't have to know all the details of that because we have a nice function that says set as input pin with pull-up resistor. We have the exact same function for pull-down resistor as well. We can specify which pin and port we're interested in there. And then when we want to get the value from the pin, we can set our variable equal to the get input pin value. So this code becomes very readable, and it means I don't have to understand all the intricacies of the registers in order to make them work. Doesn't hurt to know that stuff, but it's not really required. Okay, so that's the basics. We got input and output on a general purpose input-output pins. We do need to talk a little bit about what I've called here flexible pin usage. Oftentimes this is called muxing or multiplexing of pins. Here's kind of just an example of one of the 20-pin msp430 devices. And what you can see is that each of these pins has multiple capabilities. You can see, so for example, on pin 14, P1.1 and timer A0 utilize the same pin. Now obviously they both can't do that at the same time, so we need to have a way of controlling that. Why do we do this? Well, we only have so many pins because in the end each pin costs money, not just on our devices but on your board. Trying to be the most efficient we can, we allow multiple capabilities per pin. So that's where the term multiplexing comes in. We multiplex multiple functions onto a single pin. So part of your hardware design and software design has to take that into account. How do we deal with this? Well, we have the P1 select register. In this case, it's the select register, and it allows us to decide, am I using that as a GPIO input, output, or so is it an in-out, or is it a peripheral function? So once again, if we go look at that pin 14 in this particular device, you can see that if it's the P cell bit is 0, well then it's going to be P1.1. If the P cell bit is equal to 1, then it's going to be that timer functionality. So we've got a couple of different functions in our driver library for that. GPIO set as peripheral module function output pin, or set as peripheral module function input pin. Final summary here to the GPIO section. We have kind of this table that we wanted to show you. Now this table might look a little condensed. It's a lot of information on this table. Let me just kind of go through it quickly here for you. Across the top you can see ports 1, 2, 3, 4, 5, 6, 7, 8, and port J. So those are the different ports that are available on a variety of our devices. As we can see, ports 1 and 2, let's start over there. Ports 1 and 2 are available on all of the 3 example devices that we're looking at here. The msp430 F5529, the FR5969, the Wolverine part, and then the value line part, the G2553. They all have ports 1 and 2. And you can see up above there, port A, that's actually a way we can talk to if you want to configure 2 different GPIO ports at the same time. So if you want to do a 16-bit write across both ports simultaneously, you'd adjust that with PA. Similarly, PB, PC, and PD. But let's go back to ports 1 and 2. These are available on all the devices. And we've tried to show you, if you kind of look down, you can see there's the in, the out, the dir, a lot of these different registers that we talked about. As you get down towards the bottom, PXIV, IES, IE, and IFG. All those 1, 2, 3, 4 registers actually have to do with interrupts. That's what the I in those stand for, is interrupt. You can see that in this case all 3 devices support ports 1 and 2, and they all support those interrupt registers. That means I can do interrupts on either port 1 or port 2. If we move over to the next column, you can see ports 3 and 4. The G2553 doesn't have enough pins, so they don't have ports 3 and 4. The 5529 and the FR5969 both have ports 3 and 4. What's unique about the 5969, though, is that they also support interrupts on ports 3 and 4. The 5529 does not. The FR5969 only is the one that, of these three devices, supports interrupts on ports 3 and 4. Going over a little bit further, ports 5, 6, 7, and, well, 8 is just a 3-bit port in this case. Again, we're running out of pins. And 5529 is the only one that has ports 5 through 8. And then finally, port J, it's a 4-bit port, and the reason is those are the 4 JTAG bits. So if you're familiar with the JTAG, Joint Test Action Group, which is part of the emulation connection, we can reuse those pins for GPIO as well on the F55 and on the FR59 of these devices. Okay, a couple last things before we get started with our coding. One, we do need to include the required include files. We need to turn off the watchdog timer, and on the Wolverine, the FR5969 devices, we need to unlock the pins. We'll look at each of these quickly. So, like most C programs, if you've used libraries or things of that sort before, you know that they usually have header files associated with them. And they include, the prototypes and whatever information is needed in order to use those libraries. We've just created a single driverlib.h file. So include that one header file and everything you need for a driver library, as well as the msp430 specific header files are all automatically included for you. Then we have to disable the watchdog. I think we talked about this briefly in the last chapter, but the msp430 watchdog is always enabled. So when you come out of boot on these devices, if you don't do something with the watchdog, you're going to get reset sooner than later. So what we want to do is stop it. There was some of the register-based code that was in the original example we looked at in the Code Composer Studio chapter. Here, we're just going to hold. In other words, we're going to stop or pause the watchdog timer. And there's a nice driver library API for that, WDTA hold. And that's how we're going to really stop our watchdog. Later on in the workshop, I think it's in the interrupts chapter, we'll actually experiment with the watchdog doing its job of being a watchdog. But for now, we just want to stop it and have it not interrupt our program. And finally, the pin unlocking feature in the Wolverine devices. Now, this pin locking feature is actually available on additional devices. The 5529 has the pin locking feature. But what's important about the new FR5859 series of parts, for example, the FR5969 device, is that this is turned on by default when we come out of reset. What this really does, so there's a pin locking feature. It's really there for if you go into the lowest power modes. In the very lowest power modes, we take all the power away from the registers that drive the pins. Problem is that if we aren't driving those pins, they're not going to hold their state. So what we can do is lock those pins to whatever state they're at. And that's what the lock LPM5 is all about. Now when we come out of reset, you can do anything you want to the registers, but until you unlock those pins, the values aren't going to change. So that's what we're kind of showing below on these FR59, 69, when we do those lab exercises, if you're working with that board. And when you're all done setting it up, you want to call this PMM unlock LPM5. And once you've done that, then the pins will respond to the values you've set up in the GPIO registers. You'll probably get burned with this at some point along the line. I don't know why the LED's just not flashing. I don't know what's going on. I know I set the registers right. I can just say that from personal experience. It's like, and you go, oh, that's right. Forgot all about that. Got to unlock the pins. So it's just one of those things that you have to remember to do on these new devices. It is a nice feature. It's just you have to be careful that you make sure you do this. Lab 3. First of all, we're going to start off with a worksheet. So we're going to ask you some questions and have you write a little bit of code. It's important you do this because we're going to use that code in the upcoming lab exercise. So make sure you don't skip the worksheet. We do provide the answers at the end of the lab. So that's one thing we're going to start off with. The two actual exercises we're going to do is we're going to do an embedded hello world. Hello world of embedded systems is, blinking an LED. So that's what we're going to be doing here. We're going to do it using driver library. Then the second part is going to be reading one of the push buttons from the launch pad. So we'll get a chance to see that. When we see the buttons pushed, we'll light the LED. When we see the buttons not pushed, we'll not light the LED. Both of these are going to be done in an inefficient way. Our goal is not to make them efficient at this point in time. There are better ways to do it with things like timers and interrupts. And we'll get to that later on in the workshop. For now, we just want to learn how to use driver library and kind of get used to using GPIO. That's the end of Chapter 3.